Welcome again to my other lecture for MTH129. I've got to paste stuff down for it to work, sorry. The two things I wanted to cover today, at least to begin with, is one of my own, just something from the assignment and then on your question. So first, I just want to talk about the assignment, if that's okay. I'll go back to your question for the sampling exam. So for your assignment, I'm just about to, everything's been marked. You can actually view your marks right now in Grade Center if you will, in my grades if you want to. I'll release the assignments later today. The trickiest question by far was question 2A and B. That was certainly the hardest part for people. So I just wanted to talk a bit about that. Now, this question here is trying to show the applications of using recurrence relations to work out the time complexity, or actually you could use the same idea to work out the space complexity of some sort of algorithm, a recursive algorithm in particular. So that's where they was trying to do the application. The mathematics does get a little bit tricky at places, which is why people found the question difficult. But I just want to talk through what I was looking for. So basically you had a merge sort algorithm, which is recursive, and you have to try to work out how much time it takes to do the merging. So let M here be the number of comparisons. That's one way of counting how quickly long it takes. So let M very subscript be the number of comparisons it makes with the list of size, in this case 2 to the power of M. So how the merging works, it splits it up into 2 halves and then basically does the merge sort to each of them. And so for each of those 2 half lists, the number of comparisons required would be M to the 2n minus 1. So that 2 there, outside the M, refers to the fact there is 2 sublists, and we're just applying it to each one. So the recursion in the original function gives the recurrence in this relation. And if you explain that part in pretty much just what I said then, that would have been 1 mark. The second aspect here, you have to try together. So the other thing that merge sort does is it splits 2 parts, does a merge sort to each individual part, and then merges the 2 together. And so worst case scenario, the number of comparisons required to merge these 2 together is pretty much equal to the number of gaps that we have between the numbers. So if there is n numbers, then there's n minus 1 gap. So that's the worst case scenario. You have to have every different gap you have to do a comparison for. That's the worst case. So if you've got 2 to the m different ones, well, worst case would be 2 to the m minus 1. And that's, again, when they fully interleave, for example, is it when it happens. That's the case we're showing. So that's the worst case for how long the merging takes. It can be quicker than that. So if the lists are, if the 2 sublists are already in order, you can do it quicker than that. You can do it in less steps. There's less comparisons required. But that's sort of the worst case. So, and that's what I was looking for, the sort of 2 marks there. The other part B, was this is the recurrent relationship, and then you have to essentially want to solve this relationship in order to do anything with it. And this question was, the solution was given to you, and you had to verify it was true. So just want to rewrite this thing down. So this is the solution that was provided to you. I had to just check it was right. Now using log laws, log base 2 or to the m is just defined. That's really just defined to be m. That's the definition of what log does. So I can rewrite the whole thing more in this sort of format. It's a bit easier to use. And so we want to verify 2 things, really. Both these conditions. So you had to check that m1, which pretty much is little m to the 0, was equal to 0. So you have to plug in this thing here for little m equals 0. So you to the 0, times by 0 minus 2 to the 0 plus 1. 0 times anything 0, minus 2 to the 0 is 1, plus 1 is 0, which gives exactly what we want. So that's right. So that's the first bit. And if you could do that one, I gave half a mark if people gave that sort of stuff. The other part, which is a more critical thing to do, is to verify the recurrence relation. So the whole relation here. And if you could do just verify that by itself, okay, basically I got the mark to award people a mark, even if you got to the first part. So I just try to explain how to do this part here. So m 2m to the 2m minus 1 plus 2m minus 1. So this is the right-hand side. So replace it by our expressions we've got here. So we've got 2, lots of this swing here, but instead of m, we have m minus 1. So it'll be 2 to m minus 1 times by m minus 1 minus 2 to the m minus 1 plus 1. So just plugging it all in, that's what I mean by substituting, and then plus 2 to the m minus 1. You then start doing the products. You got 2 times this one gives you 2 to the m minus 1. 2 times 2 to the m minus 1 is 2 to the m. 2 times 1 is just 2. So we give all these sort of terms, and you can see lots of things start to cancel out. So the 2 to the m's cancel out, the 2 and the minus 1 cancel out, giving you just a plus 1. And then you can expand the brackets. This gives you 2 to the m minus 2 to the m plus 1. But that precisely is this expression over here, which is m to the 2m, which is the left-hand side. So the whole idea of subbing into equations really is just plugging into one side, and then just make sure you get the other side. What the difficulty here, particularly as I wrote it around in the first way, was the logs, which so as I was doing the solutions, it dawned on me that giving that second form might have been more beneficial to students. So I'm sorry I didn't do that earlier, but that's sort of the verification of that process. So if you could do all that, that was the 1 mark. But the whole purpose for this was to show that was the solution, and therefore you could work out what the solution was in general. And then the other steps weren't as difficult as that. And you had to go, what's the big O for this? Well, the n log n dominate. So this is the big O of n log n. A selection sort, for example, is big O of n squared. So if you had a really big list, then using the n log n is a cheaper cost than n squared. So therefore, the merge sort for bigger lists would be preferable to a selection sort. It's sort of what the next few questions are about. Just some warnings though. Any recursive function, how recursive functions work is they keep track of where you're up to, like which particular function call it is. Like if you call a function multiple times, working where you're up to by pushing all the stuff onto the stack. So there's a stack in memory, and in the stack, it keeps a record of the local variables for that call of the function and what line it's up to. And once it's exited, when it returns to the function, it just pops back off one thing off the stack to go where it was before. And so if you've got lots of recursion, it means that stack is full of functions essentially. So you're using more memory. And so high level of using lots of recursion uses more memory, and that can slow things down as well. And so recursive functions are much easier to program, but they can have a hidden cost of memory usage. And that's always a danger with them, particularly if you have lots of instance variables, which are local variables. So they come with a cost, but nevertheless, despite that, merge sort normally is so for bigger cases it is superior to other sort of things. And so as I alluded to before, the Java, for example, if I'm remembering properly, uses something called tim sort, which is actually um, for small cases does something a bit different, gets runs, but for larger cases, really it's just merging. So just really merging some all lists together. So a tim sort is a merge sort with a little variation for the smaller cases. So when it gets smaller, it does something different, and it's not looking for runs, and it does that more by a sort of selection sort. So it's a hybrid scenario. Trying to get the best of both worlds is the idea. So that was the part of the assignment 2 that I really want to focus on. Um, the other parts, if people did them, most people did really well, which is great. Um, and again, the exams are more like those questions. Probably good for you. Some other question that Dylan here's got is this is question 5 from the sample exam 1, and it says give 2 examples of a Boolean algebra. So a Boolean algebra basically is some sort of pattern, and you need to identify what the pattern is and how something matches it. So the easiest example of a Boolean algebra is a subsets of U, for example. That's one example. So you've got one example of subset is a collection of subsets of some universal set. Or putting another way, it's the power set of U. So first thing you need to give is what all the different things might be that make up the Boolean algebra. Then you just tell me what each of these sort of corresponds to. So there's 5 key things in the pattern. You just have to identify them. So the plus corresponds to union. You can say that. So U or union. Multiplication corresponds to intersection. Overline corresponds to set complement. Zero corresponds to the empty set, and 1 corresponds to the universal set. So pretty much there's the 6 things. One I have to name what the actual Boolean algebra is, so the collection of stuff. And then for the 2 binary operators, I have to tell what they correspond to, and the overline complement corresponds to, and what 0 and 1 correspond to. And that's just showing what the pattern is. So the other key example that we did, apart from sets, was logic. So propositions, with true false values, and to be more precise, I mean, that's true. Propositions with true false values is the basic idea we looked at. You can consider them especially by the number of different basic units you have, the atoms. So how many different letters you're allowed to make up their proposition from with. But the plus will correspond to or multiplications, and overline is not. 0 is false and 1's true is the pattern. And they're the 2 key examples we did. We did others. So we did binary numbers. So looking at binary numbers, so the set of all subset, you can just do the 0 and 1 by itself. Plus and multiplication correspond to, so plus corresponds to finding the maximum of all the values considered. Multiplication. Overline is swapping 0s and 1s around. 0 is all 0, 1 is 1. So there's lots of other examples. I did others, but these are the 2 key main ones that we looked at. And so part 2, interpreting this equation each of your samples, which is the absorption property. So this first one would say you've got a set A intersect with a union B is equal to B. That with the interpretation in terms of sets. So if you've got a union intersects with one part of it, you get A again, not B. And in terms of propositions, so you get a proposition P and P or Q, then you get back to P again. That would be the same sort of idea in terms of propositions. So that's what I and I are sort of on about. Does that answer your question that you had, Dylan? So as I said, Boolean algebras are sort of a pattern, and certain things match the pattern, and when it matches the pattern, all the rules nicely apply. Yeah, awesome. Any other questions you've got from the sample exams? So I did most of 2 in there. Pardon me. Okay, no. So, no one else has asked me any questions to cover today. So I'll just do a brief critique on this, and then I'll leave it that more for practice for short. As I said in my lectures, your final exam looks something like this. I try to make it slightly shorter in terms of length to what these sample exams are. Similar sort of coverage and content though. They will have marks, so utilize that to your advantage. You are allowed to bring a formula sheet in, so please make the most of that. I've given an example one which you could utilize. And so, print that out and use it if you want to, or you can update it. That's fine. There's a few times when these things are slightly different to what we might cover. And more if you can more see in the second one. So I'm trying to think what so things like in your exam, question 4A, I would just say solve the recurrence relationship by a method you choose. I wouldn't force you to do it one way or the other. I certainly wouldn't force you to do it twice in your exam. So you can pick either or. And also for big O sort of stuff, my focus has much more been in terms of your assessment so far, and that will be true in the exam too. Not to look at the formal definition of big O, but more be able to utilize it. So questions more like C part I rather than C part II, for example. They're the main differences between your exam and this one mentioned here. It's an exam is only a subset of all the questions I could possibly ask, so I can't ask everything. So there's some bits in these exams that you won't get asked in your exam for lack of. It's only a 3-hour exam. On the other hand, there might be some things that aren't in either of the sample exams I might ask, but still in the content for the subject. So it's worthwhile you guys to practice it in yourself. So in terms of when I did these things in tutorials, I mostly just let students do questions themselves. And again, I encourage you to do the same. If you get stuck as you're going through it, there are solutions, but come and speak to me if you need to. And people have been doing it, which is great. The only thing that's worth mentioning is I made a mistake in that formula sheet, which I should mention an announcement about the tree traversals. So for a pre-order and a post-order, I got the corresponding postfix and prefix notations around the wrong way. And if you read through it, it goes, oh, that looks wrong. So too many copy and pasting, I think, when I did that. But otherwise, the formula sheet is good to my knowledge. But if not, let me know. So that's all I was planning to do, unless you had other questions, Dylan, today. So other things, please do the evaluations. I'd like to know what your feedback is. And more important than anything else, good luck to your exam and hope you go to your ability. But I think you'll be fine in general. If you've been turning up to lots of classes, you're going well. If you've been listening to recordings, you're probably been going well too. If you have any other questions, fire away.